All right, can you guys hear me okay?
Yep.
Yep.
Outstanding. And I've got, all right, the mic selected. We should be live on YouTube. Make sure I mute this one. All right, so somebody who's responsible in the participants window, raise your hand if you're responsible. And now to tell time. Really? There's no hands coming up? There's one. Sam. All right, Sam. Your job is to interrupt me at 11:35
Okay.
and remind me that from 11:35 to 11:50, I'm going to answer questions about the quiz in case people are having trouble setting up some of the problems. So remind me at 11:35 that that's what we're going to do.
Okay.
What else? Looks like we got most of the people logging on. All right, so I'm going to go ahead and get started. What, where, when? I move this up to this screen. All right, then I can see that, and I can see this. What does it mean to what does it mean to you guys if I say design for manufacturability?
I think of can you hear me?
Yeah.
I think of making a design that it won't cause unnecessary wear on machine tools, or it doesn't use an overly complicated process for machining.
So doesn't cause unnecessary wear. Extra.
We can't.
I'm just not sure I can spell it. Yeah, I'll switch. I'll switch cameras in a minute. But no unnecessary wear and no extra setups. Is that what you said?
Yeah, I just said something that's not overly complex, so it's relatively easy to mass produce.
Not overly complex.
It's made with the machining in mind.
Can you say that one again?
It's made with the machining processes in mind.
So made with, I'm going to say with the manufacturing process in mind, because we might not be machining it when we're designing for manufacturability. This marker doesn't work very well. Made.
Something that's like you don't need to do a bajillion of like steps, or you don't need to like have to pre-make a fixture for it.
So I think that's covered with not overly complex. Made with the processes in mind. And when you said made with the processes in mind, you meant designed, right? So designed with the processes in mind. Let me switch screens here. You guys should be able to see what I'm writing on the whiteboard now?
Yes.
Okay. So doesn't wear out the machine tools quickly, not overly complex, designed with the processes in mind.
The tolerance is achievable.
So tolerances, I don't know why tolerances started with a D all of a sudden. Are achievable. I actually like the way you said the tolerances are achievable. A lot of times we automatically think when we're designing for manufacturability that we just want to have the loosest tolerances possible. And that isn't really true, because when we talk about functional design, you remember, we didn't just want to have loose tolerances to make it easy to make. We wanted to have tolerances that would meet the functional need. So that's why I like achievable, because it's possible that an extremely tight tolerance is what's required to make the part function. And if that's required to make the part function and there's no other way to solve that problem, then it just needs to be achievable. So you need to be able to conceive of a manufacturing method that would meet that tolerance. So I really like the way you phrase that. Is there anything else that comes to mind when we talk about design for manufacturability? I mean, we've been talking about manufacturability now for like, or manufacturing and manufacturing processes for like, what, 5 weeks, 4 weeks, something like that. What else comes to mind if I say I want you to design this with manufacturability in mind? So design for manufacturability.
Well, sort of in the same vein as like the achievable tolerances, something that we talked about with like the piece where we're testing the surface roughness is like, don't over constrain the design.
So don't over constrain. Or don't over define. Right? The CAD software typically tells us that we've over constrained something when we specify too many dimensions. But it's really over defining. What's the real cost of over or under defining on the art, right? The art is the thing the designer sends to the manufacturer. What is the real cost of over constraining or over defining the specifications?
Basically, like if you over define it, it's not gonna be clear of like, okay, which of these tolerances that are defined are the most important to achieve.
Aren't you going to waste time like
So
designing?
if it makes it unclear, if you are the manufacturer and you have received a design from your customer, so let's say we were a job shop or a high mix manufacturer, you've got a customer who is the designer sends you the specifications for their part. And for some reason, the specifications are unclear. I don't know why I put unclear on 2 different lines there, but again, I'm an engineer, not a grammaticist. What happens if you're the manufacturer and you receive unclear instructions from the designer?
You're going to make an error, so you can.
So
the repeatability, the ability to repeat the same process will be taken away almost.
I don't think it impacts my ability to repeat. If I'm the manufacturer and you give me instructions that are unclear one time, I have to make a judgment. I have to decide what it is you meant as the designer, but I should be able to repeat that as long as I set up the process once and I don't keep making that judgment over and over again. I think I should be able to keep repeating that, but I may repeat it 10,000 times and make something that isn't what you, the customer, want. So the risk is that I make parts that don't fill the customer need if I make judgments. What do you have to do then if you're the manufacturer and you get unclear instructions from the designer?
You have to go back to the designer, which would, then increase like labor costs and whatnot.
So if you want it to be clear, you're going to have to iterate with the designer. And sometimes that's really difficult. I have a story of a part, and it was a part that our company was making, and we got the job. So when I bought the company, for the 6 months before I bought the company, I worked for them for no salary. And then for the 6 months after I bought the company, the previous owner worked for me for no salary so that we could trade off the knowledge that it took to run the company. So we got in a request for a quote from an old customer, and the previous owner did the quote for us. And he said, yeah, that part looks like the part we used to make for you guys. We could do it for the same price. Now, I, as the new owner, I said, oh, well, if you believe we can do it for the same price, I believe we can do it for the same price because you know way more about this. You owned this company for 30 years. So yeah, we'll quote it for that. And then we found out after we had the purchase order in hand that the design was significantly different from the old part. At this point, we're stuck with it because we agreed. But we had put in that we haven't made exactly this part. So we put in, actually, it was a $200,000 order. $25,000 of it was to figure out how to make the first part. Because we knew it was going to be hard. We just didn't think it was going to be harder than making the old ones. And so $25,000 to make one piece. And then I think it was another $200 at $500 each after that. So at that point, we're very critically going through trying to make the part exactly as it was designed. So we can make that first proof of concept part, that first article, do our first article inspection, send it to the customer, let them do their first article inspection on it to make sure that we agree on all of the features. And we had, I don't know, probably 2 weeks into the manufacturing process in designing processes, figuring out how to make it. We get to that step where there was a tolerance that was unclear on the drawing. And that's easy. You call up the customer, right? Especially when it's such a critical part. Call up the customer and say, hey, this tolerance is unclear on this dimension on this drawing. What exactly is it you mean? So that we can make sure that we make it the way you meant for it and that we do our inspection so we will measure what it is you mean. And the engineer looked at it and says, well, that feature is not on the part. They had given us the wrong drawing. They gave us a drawing for a different version of the part, not the part they wanted to buy from us.
Oh no.
But we're already
that's brutal.
3/4 of the way into the $25,000 of the first part of the order. Now, it turned out that it was possible to salvage that part, and we made everything work, but it cost us a week of production time to go back and figure that out. We couldn't charge extra for that week of production time either, because one, it's a new relationship with a customer, and so although it was an old customer for the company, that's, you gotta treat them like they're a brand new customer when it's a new owner. And anyway, so that uncertainty, so we were unclear by the tolerance. If we hadn't been unclear about the tolerance, we would have made the wrong part. We would have shipped it to them with our inspection certificate, and they would have said, well, this isn't the part we ordered. And then we would have had a dispute, right? So communication with your customer can help a lot, but when the customer is unclear, it certainly makes it cost more to make the part, even if the manufacturer can't get paid more. It costs the manufacturer a lot of money if the customer's unclear. It can cost the manufacturer and the customer if it's unclear. If we're trying to design for manufacturability, is there anything else that comes to mind? We want to, and so this no extra wear just means it's going to be cheaper to make the parts because the machine tools won't wear out as fast, right? Or the tools won't wear out as fast, or whatever it is. Anything else that comes to mind? I actually think we have a pretty good list here. If we're conceptualizing the idea of designing for manufacturability, we don't want it to be overly complex. Honestly, when you design for functionality, you don't want your things to be overly complex either, because the complexity is also like the information content, the amount of information that's in the part. And typically reliability is inversely proportional to complexity. So the more complex, the less reliable something will be. Design with the processes in mind. So I think many of you, probably at least half of you, have taken a class in design at WPI. Is that true? Raise your hand in the participants if you've taken a class in design. I don't know how long the hands stay up, but they seem to be coming in pretty quick. So a bunch of you have taken a class in design. Somebody that's taken a class in design at WPI, Did they talk to you about the processes that would be used to make the parts that you were designing?
In like
Yes,
the
but-
sense of CAD, I would say like you learn how to like chamfer and stuff. So like you don't necessarily know the part, but you know the process.
All right, so in your CAD class, you learned about chamfers. What did they teach you about chamfers in your CAD class?
Like just the dimensions of it kind of, and then like
So they taught you how to
execute
specify the
it.
chamfer.
Yeah.
Okay, that's good. Why do we put chamfers on parts? And you guys know the difference between a chamfer and a fillet first? So if we
A
have,
fillet is round, right?
right, if we have the corner of a part here, so let's say, I don't know, what kind of a part is it? It could be this part, right? This is a little adapter that plugs into a Surface laptop to get a HDMI port out of it. But say we were designing this part of it, and where you see the edge here, can you guys see this, by the way? The white
Yeah.
part with the white background. Let me get something that has some contrast. Oh, something boxy that has some contrast. Here you go. Here's a box. You can see this, right? So it's this little magnetic ball and connector thing. It's really cool to play with, by the way. So you've got the edge that comes over here and then comes down here. So you get these two edges that meet here, and it looks like there's a 45-degree angle between them. Did you see that here?
Yeah.
So that angle between those two edges, that's a chamfer. And so if we were drawing it in the cross section here, we would just take that corner off of the part. So that's a chamfer. If instead of making an angle there, my fingers don't erase this very well at all. If instead of making that angle there, if we made it round with an arc, that would be a fillet. So that's the difference between a chamfer and a fillet. In your design class, they probably told you to draw the chamfer. Did they tell you to draw the chamfer or draw the intersecting things and call out the chamfer?
I think it was the intersecting things and call it the chamfer.
Because you can do it either way. I often in drawings and solids that I received in the last, I don't know, 5-10 years, they almost always draw the chamfer and call it out. But you can do it either way. So you could draw the box, and you can have a call out. And you'd specify chamfer in maybe 45 degrees and some length 0.030, something like that, if this was inches. And so what they're saying is they want this dimension to be 0.030 inches here, and this angle to be 45 degrees. The other way you might see that is just like this with the chamfer call out. But another thing that you might see is a note on the drawing. Break all sharp edges. What's the purpose of a chamfer on the outside edge of the part?
Is it to get rid of sharp edges?
It's
'Cause they
almost always to get rid of sharp edges that are left over because of a machining process. So if we were making this box and it didn't have a chamfer on it, we would very likely do a side milling operation here, where the end mill, right, the end mill would be spinning and it would feed towards us and it would make this surface that we see the edge of here. And maybe a facing operation where our end mill would go back and forth across the top and it would make this surface here. Right where that end mill comes off the edge when you're making that surface, a little bit of the material. Remember when we did the cutting in the lathe and we did the cutoff operation, there was that little nub of material that was left standing out, right? So when we're doing this, so before the tool gets over here, there's material in the way. As the tool gets over here, eventually the cutting force will be so much that instead of breaking off or cutting the material, it folds it over. And you'll end up with a little sharp edge, a little sharp corner there called a chamfer, or sorry, a burr. And so on most 90-degree or roughly 90-degree corners, you'll end up with a burr like that if you don't do something about it. So the reason we started putting chamfers on parts in the first place. That's cool. Am I playing music or is somebody else playing music?
Someone else.
Huh. I've never been serenaded during lecture before. We put the chamfer there to, I hope that was somebody's ringtone and they were getting a phone call. That would be cool.
So for the
you put the chamfer there to get rid of that sharp edge. Now, what if you're sophisticated about this, what you'll realize is you've really made the sharp edge smaller and you've moved it down to here. But it'll be less sharp, or it'll be much smaller and less sharp because it's that 45-degree angle.
So you should do like the chamfers last in like the cutting operation order?
You will be able to tell the difference by running your finger across the corner if the chamfer was done last or not. Sometimes we do the chamfer earlier just because of accessibility issues, or sometimes we like when we put a chamfer on a hole, if we're machining the bottom of the part, but we're going to drill the hole from the top side, we often will pre-chamfer where the hole is going to come through. And that's just for convenience in manufacturing. If it really mattered, if you couldn't have any burr there, then you'd need to do some kind of a secondary operation afterwards.
So the difference between this and the fillet would be just the roundedness?
So in a fillet would be rounded. The functional reason for a fillet typically would be the same as the functional reason for a chamfer. In CAD software where you're doing your solid modeling, there's when you make the fillet or the chamfer, there's an option. Usually it's extend to all connected faces or something like that. Is that on there still? And it blends those fillets together, right? And it looks really cool and swoopy and all that stuff when you look at the part. Has anybody experienced that?
Yes.
Yeah. How do you make a fillet on this edge to start with? We'll get to the swoopy and blended together part in a second. But if you wanted to make a fillet right here instead of a chamfer, and you were doing the manufacturing part, not the design part, what tool path would you use?
You'd need a circle that was tangent to both edges.
So you could build a tool shaped like this, a cutting tool shaped like that, and come in, and so you make both edges and then you could run that cutting tool along the part. You could do that.
You turn the part sideways and you just draw a circle around it.
You could flip the part up on end and have a tool path that goes around the corner. You could do that. How else could you do it? I can think of one additional way.
Could you do like the freeform operation on it?
You do a freeform operation like you do in the Y block, and you get a tool that's shaped like this, and you go through here, then you go through here, then you go through here, then you go through here, and just like on your turned surface, where after the tool feeds past, you end up with a surface like this left behind. If you do this with a ball end mill going back and forth, you'll end up with a surface like that along the edge of the part. How do you make the little curvy bits on either of these surfaces smaller?
More passes.
More passes. Here you'd have a smaller feed per revolution, right? Here you'd have a smaller step over per pass. And one of the things in a spree, when you're creating an operation like this, it allows you to actually specify the maximum scallop height. And so you can actually specify the maximum scallop height, and it will, based on the tool radius, or the radius of the ball end mill, based on that tool radius, it will figure out how many steps it has to make. It will actually space them unevenly, because as you come down the side, you don't need as many close together. So you can do that. Of all of these processes, which one is the fastest one to do?
The first one with that tool bit?
The one where you make the custom tool and just run it along the edge. If you have...
Are we including the making of the custom tool in it? Or like...
Well, no, I'm talking about the operation of the practice, because you can
okay.
this. If you have
that
a
one.
bunch of different radiuses called out on your part or your part family, then in order to most efficiently make the parts, you'd need to have a lot of those different tools, right? You need to have a lot of those special tools.
Right.
If you call out chamfers of different sizes, how many tools do you need?
One.
Right. You can make all of the outside chamfers with the same tool, regardless of how big they are. I mean, even if your chamfer tool, which typically looks something like this, even if your chamfer tool is only this big, and you have a chamfer that needs to be this big, you can still make it with that tool by simply stepping down a couple of steps. So, if you're thinking about designing for manufacturability and you have no functional reason to have a fillet instead of a chamfer on the outside edge of the part, should you put a fillet or a chamfer?
Chamfer.
Because you know that on average, it's cheaper to make the chamfer than it is to make the fillet. Now, it looks cool, a functional reason to have the fillet?
I think it depends on the application.
It totally depends on the application. If the customer will buy it if it has the fillet and won't buy it if it has the chamfer, then the fillet is the right design choice. If it helps you differentiate your part from the competitor's part, it makes the customer think that your part's cooler, that's part of the value in your part, right? So the way it looks, the aesthetic value of a feature can be functional. It's hard for the manufacturer to know whether or not it is. So if you call out fillets instead of chamfers, almost no manufacturer would come back to you and say, hey, it'd be cheaper if we made a chamfer instead of a fillet there. Because they don't know. It's up to the designer to decide what's important. So as the designer, you want to think about those things. All right, so that's cool. What if it was a pocket inside the part? And so if we were top-down view looking at a pocket, and we were doing this, so we typically make that pocket by taking an end mill of some size, right? And going around in some pattern inside there. So if it was a pocket in the part, what are the special design considerations we might think of if we're machining this?
Size.
The size of the pocket, you mean like the dimensions here? Call that one Y and this one X.
Yeah, or yeah,
so certainly the size of the pocket and the shape of the pocket matter. It doesn't have to be rectangular. I just drew it rectangular.
If it has islands.
Are there any islands in the pocket?
The four corner.
Right. The thing I was getting at was these four corners. What's the minimum radius that this corner can be?
The smallest milling tool you use.
The minimum radius that this corner physically could be is half the diameter of the end mill that you plan to use to make it. Or the radius. But I always, when I'm talking about that dimension on an end mill, I always say half the diameter. Because when I'm talking about the radius on an end mill, I'm always talking about the cutting corner down here. Because we often put a radius on that so that it wears predictably. And if it's a ball mill, the whole bottom is a radius. So I'll say half the diameter, the maximum. Now, do you even want that end, so the radius to be half the diameter?
Probably not.
Probably not. You actually want it to be bigger than half the diameter, because when it's exactly half the diameter, draw my end mill here. See if the purple works. So if it's exactly half the diameter, the tool path that makes it will look like this. And as the tool comes to here, it gets to that spot and it stops momentarily, and then it moves the other direction. At the moment when the end mill stops here, and it's really just a momentary hesitation, the moment when that end mill stops there, and if you've been in the lab when somebody was making a part like this, you've heard the noise. There's a very screechy noise that comes from the end mill, because suddenly it's still rotating very fast. Suddenly it's burnishing the part instead of cutting the part. And then it starts cutting the part again. It wears out the tool prematurely, and it leaves horrible looking marks in the corner of the pocket.
Hey,
But
Professor.
if it's
Professor.
The end mill's a little bit smaller.
Professor.
Yes.
It's 11:35.
All right, sweet. If the end mill's a little bit smaller, then the tool path will have an arc to it, and you'll never get that screechy bit. You won't wear out the tool, and it won't be horrible. All right. Tomorrow in lecture, what's tomorrow's scheduled activity? Metrology. Tomorrow in lecture, I'm going to continue talking about this design for manufacturability some more, and then we'll get into the topic of tomorrow's lecture. But I wanted to give you guys a chance, if you have questions, to ask me specifically. I have been consulting on some questions that have been going in the discussion forum and being asked to some of the PLAs and the staff. But is there a question from the quiz that somebody has a specific question for me about that we can work on?
From this last quiz?
Yeah, the one that's due tomorrow night.
Just like setting up question 9.
Read to me question 9.
Um,
I just don't remember which one is which.
For a given turning operation that is the maximum allowable cutting force in newtons, if the clamp force is 5,000 newtons, the fraction of no, yeah.
All right,
fraction,
so we've got. All right, so tell me what the given information is.
clamping force is 5,000 newtons.
So I'm going to call it F sub C, 5,000 newtons.
I'm assuming it's supposed to be friction, even though it's this fraction coefficient.
Yeah, the fraction coefficient, friction. U.
Between chuck jaws and parts is 0.8.
Okay.
Spindle speed is 3,000 RPM. Mass of the chuck jaws is 0.6 kilos. Diameter of the workpiece is 100 millimeters.
Now, you may not all have the same dimensions for all of the parts, but all right, so we've got this clamping force. So we're squeezing with hydraulic pressure of 5,000 newtons on the part. We know that the friction coefficient between the workpiece and the jaws that are clamping it is 0.8. Our spindle speed, program spindle speed is 3,000 RPM. The mass of the things that are doing the clamping is 6 kilograms, and the diameter of the part or where the clamping is 100 millimeters here. And what they want us to find out is what's the maximum allowable cutting force. Is that right?
Yes.
All right, so the first thing I want to do is understand what is the maximum allowable cutting force going to depend on. And it's going to depend on how much friction force is available between the workpiece and the chuck jaws. Does that make sense? So if you have cutting force that exceeds the friction force that's possible from the normal force to the chuck jaws, then the part will move in the fixture. If the part moves in the fixture, we have too much cutting force. That make sense?
Yes.
So how much normal force is available?
5,000 newtons.
5,000 newtons minus the
Before we
centripetal
start
force.
spinning the spindle, 5,000 newtons is available. As soon as we start spinning the spindle, let's say if it's a 3-jaw chuck, and we didn't tell you in the problem because it doesn't matter how many jaws. But if it's a 3-jaw chuck, when I start spinning the spindle this way, what do these jaws that weigh 0.6 kilograms want to do?
Want to spread out due to the
They
spin.
want to spread out, right? We have centripetal acceleration. So as the velocity goes this way, the jaws want to go this way. What's the centripetal acceleration going to equal?
Velocity squared over radius.
It's going to equal v squared over r. Acceleration is going to equal v squared over r. As they accelerate away, they're going to reduce the clamping force by mass times acceleration. So if you spin this, it accelerates away. And so what's velocity? Radius is given, right? It's half the diameter.
Would velocity be the 3,000 rotation? No, or that would be the.
What you need to do is you need to take your 3,000 RPM
And convert it from.
and your diameter, and you need to make this be surface speed. And you need to make sure that your velocity units and your acceleration units allow you to convert to newtons when you multiply by kilograms. So you'll have to factor in conversion factors from millimeters to meters, I think, and maybe from minutes to seconds. What's a newton again? And it's a measure of force, but how do you break
Kilogram
it
meter
down?
per second.
Newton meters per second? No,
Yeah, or kilogram meter per second.
kilogram meters per second. So you want to make sure that when you find your acceleration, multiply it by mass, you end up with kilograms meters per second. Then you want to take that, you want to subtract it from your 5,000 or whatever number you've been given up there. And that will tell you then the maximum friction force which you could create, which then will equal the maximum cutting force. Is that clear then?
Excuse me, Professor. I think it's unit for newtons is kilograms times meter over second squared. Because
Is
it's
that what I wrote?
acceleration. So, yeah. It's just the seconds on the denominator.
Oh, seconds are squared. Yeah. Sorry. This is one of the reasons I don't quote the formulas myself when I'm writing them on the board, is because I make stupid mistakes like that. So thank you. I always try to take dictation when it's about putting a number or something on the board. That way, if it's wrong, it was you guys that screwed up, not me. Sometimes I'll even write it if I notice that it's wrong to make sure somebody finds the mistake. But I won't do it on purpose without telling you there was a mistake. Probably. What's next?
Professor, I have a quick question about the roughness lab.
Okay.
What are we dealing with rolled aluminum or cast aluminum? Because there's different constant values in the book for them.
Rolled.
All right, thanks.
What's the initial diameter for the stock that was used for the roughness lab?
Before the roughing pass or after the roughing pass? The initial diameter of the stock material was 1 inch.
Okay.
Where we're doing the measurement part of it, measure the diameter off of your workpiece and use that diameter. And since I know it changes across the workpiece, use the average diameter of that section.
Okay.
Does that make sense?
Kind of.
I don't have one of those right here, but if the part looks like this, so here's one roughness section, here's one roughness section, here's one, right? So measure the diameter here, the diameter here, and the diameter here, and use those diameters. And again, we're estimating. So if you use just this diameter for all of them, or just this diameter for all of them, or even the smallest diameter for all of them, it wouldn't make your estimate off by so much that it would matter.
Okay.
But just note what diameter you used so that somebody could repeat the experiment later if they just saw your steps.
Okay. And then, but like for the roughing pass, like that would have been like one, because you gave us the depth of cut.
Yeah. The depth of cut, I think, is 0.5, right?
Right. Yeah,
Yeah.
so basically once we get those diameters, just work backwards on the initial.
Yeah.
Okay.
Do you need the initial diameter?
I think. And for one of the
I think it
places-
depends on how you set up the problem. I think you could
Yeah.
probably solve it without that.
Okay.
And again, this is about making the observations and reporting the observations and drawing conclusions from that. So as long as you show how you set up the problem, if there's discrepancy between your group and somebody else's group, that's not going to matter as long as you've showed the process.
Okay.
It's not this. The understanding is much more important than the precision in this, or the accuracy. I feel weird because the camera's over here, but you guys are over there. So I keep looking to the side. Is that my good side? I don't know. Anything else? Looks like there's something in the chat. Let me check that out. Nothing important in the chat.
Professor, what do you mean by group? Is there a group project?
Yeah, you're supposed to be working on this with the group that you were assigned to in the beginning of the class.
So, are we submitting one report? Is that what you mean?
One report per group.
Okay.
And when is this due by?
I think we put Friday this week. Anything else?
Yeah, Professor, there on the website for week 5, I believe, I don't see any of the virtual lab work posted, like the PowerPoint presentation. Usually it has like slides.
I will copy that over. Yeah, I just wanted to get the thing up there so people had a link for today's lecture. I will copy that over, but we're focusing this week on making sure that you get your hand-in CAM assignment done. There are some new assignments that I'm going to put out there. They're not going to be graded. They're for you to learn.
Okay, thank you.
So if you have not yet handed in your hand-in CAM assignment, please be working on that. And anything else?
Just for the hand-in CAM assignment, when do you think like the feedback would be back on that? Because do you say we could like resubmit it with edits or?
Yeah, definitely all of them will be graded by the beginning of next week. I have the ones that have been submitted. I asked somebody to start grading them today.
Will we be getting our quiz grades back soon?
I'm almost finished commenting on everybody's essay answers.
All right, thank you.
I don't want to just give you a grade without telling you why I chose that grade. So I've been going through and reading and responding individually to people's answers. So it took longer than I expected. So that should be back shortly.
Does it still stand that we can like take them again to get a higher grade if we want?
Yeah, I don't think there's many people that need to do that though.
Yeah, but okay, thank you.
Professor, do we have to hand in the CAN Chapter 6 getting started?
No. That slide was supposed to be deleted. At the end of the Y block part.
Yes.
Yeah, no, you don't have to hand that in. We had some debate whether that or the one we asked you to hand in was going to be the hand in assignment. We decided to go with the base part instead of the Y block part. Anything
If
else?
we have further questions for like the quiz or anything, who's best to email? Is it the TAs or you?
Me, but there should be a discussion forum in Canvas.
Oh, there is.
Yeah, I'm just double checking to make sure there is. I think there is. If there isn't, I'll create one. The discussion thread, or I think you guys can create threads yourself. So if you have a question about a quiz question,
Okay.
if you ask it there, then the whole class can benefit from the answer.
Right. Okay. Thank you.
And I think we've caught the mistakes in the automatic grading in this quiz in past terms, but it is possible that you have the correct answer and it's being marked wrong. So if you're confident that you did it correctly and it's getting marked wrong, just let us know and we'll figure it out. And if you didn't go outside yet today, don't. It's cold out there.
And very windy.
All right. Thank you. That is very true. It's freezing.
It was like 12 this morning when I got up, but it's going to get warmer and warmer and warmer as the week goes on.
Thank you very much.
Pretty soon we'll be setting up the pool again, right?
Professor,
Yeah.
I was having some problems with the CAM software. I was having trouble like moving the processes from one file to another.
Were you talking to a PLA about it?
Well, the problem is I can do it, but my computer doesn't have enough RAM to complete some of this stuff, so I'm not really sure.
Before you copy the process over, go into the process and turn off the stock automation feature.
Okay.
And if you do that when you get the out of memory error message, turning off the stock automation usually fixes it. And I think, yeah, I've seen that message before. I'm not certain if it's a bug in the software or if it's a bug in our computers.
All right, I'll try that. Thank you.